Hi. Geologists for a long time were able to use relative dating to work out that some rocks were older than others, and perhaps even to get some idea that geological time was huge. But to actually work out exactly how long geological time is, exactly how old um, geological events are, is something that is perhaps a more recent discovery. Even then, our understanding of this has changed. This picture was taken in Minnesota in USA, um, and the sign here is a little bit old. Um, this was true when I was studying geology at school like you are. As we'll see, it's no longer the case. We've actually discovered rock that's even older than the 3,800 million years that this particular granitic gneiss is. So the question is, how do we actually work this out? And we can measure the age of rocks, or should I say some rocks, by using a technique we called radiometric dating or absolute dating. This uses radioactive minerals that we find naturally occurring within rocks. Let me give you an example. If we have a mineral that contains uranium-238, so a type of uranium, that element is unstable. We call it a parent element. Because it's unstable, we'll get some radioactive decay. We'll get particles released from that uranium that will change it. That gives out some heat. It's why we can use nuclear power stations. But it will change the uranium into what we call a daughter element. In this case, it's a type of lead, lead-206. Now this change, going from uranium-238 to lead-206, happens at a fixed rate. Nothing changes that rate. Heat, pressure, time, nothing changes the rate at which that happens. It means we can use this reaction, this change, as a clock in a rock. Now these different types of elements are called isotopes. Isotopes comes from Greek words that means the same place. And what that means is that these elements are found in the same place on the periodic table. So for example, I've shown you there some hydrogen. There are three different types of hydrogen, what we call protium, deuterium, and tritium. Now, those three isotopes are all hydrogen, but there are subtle differences between them. Now, in geology, we use a small number of these isotopes. Let me show you what they are. So uranium we've mentioned already, that changes to lead in a couple of different ways. Thorium will also change to lead, but a different type of lead. Potassium will decay to argon. Rubidium changes to strontium. And finally, carbon-14 changes to nitrogen-14. These are the changes that we use to determine the ages of rocks, because we know how quickly each of these radioactive elements, the parent elements, change to their daughter elements. So having seen all these changes, if we look at how long they take, this is a list of these elements that we use in geology. I should stress you do not have to remember this off by heart. You have to understand how the process works. You do not need to remember all of these numbers. You can see that each of these changes, each of these reactions, takes a different amount of time. They have different what we call half-lives. So uranium-238 has a half-life of 4,510 million years, about the same age as the Earth. Rubidium to strontium, though, has a half-life of 47,000 million years. Huge amount of time. Now, the technique that most people have heard of is carbon dating or carbon-14 dating. That has a half-life of 5,730 years. It's an extremely short amount of geological time, and that limits massively what we can use carbon-14 dating for. More of that later. Okay, what I'd like you to do is do a little experiment for me. You need to get yourself a coin, or ideally 40 coins, but one coin will do. And what I'd like you to do is I'd like you to toss that coin 40 times. I'd like you to record how many times that coin comes up heads. Write that down in the table at the top of page 19. I'd then like you to toss the coin again, but I'd like you to toss the coin for the number of times that heads have come up. So for example, out of the 40 coin tosses, say 23 times it came up heads. So you write down 23 for your first attempt. For the second go, I'd like you to toss that coin 23 times. And you keep on going then till we get to 0. Once you've got those numbers, I'd like you to plot them on that graph. Okay? And join the dots up with a line. Have a go at that now and see what you come up with. Press pause and toss that coin. Okay then, let's have a look at some of your results. So having tossed the coin, what we should see, roughly, although it will vary, is that every time you toss the coin, the number of heads that comes up should be roughly half of what you tossed. So if you toss the coin 40 times, you'd expect 20 of those to come up heads. If you toss the coin 20 times, roughly 10 should come up heads. So what we'd end up with are points on a graph that look like this. If we join those up with a curve, we see a shape like that. Your graph should look something similar to that, although there will be variations. This is what we call a decay curve. And it's this decay curve that allows us to work out the age of rocks. Because just like a coin will turn up heads about half the time, so in radioactive decay, the time it takes for half of those radioactive elements to decay will be a fixed thing. That's the half-life. So if we start out with 1,000 atoms of uranium-238, after one of its half-lives, we'll have 500 atoms left. And 500 will be the daughter element. After 2 half-lives, we halve that again, so we then have 250 atoms of uranium and 750 atoms of lead. And it just keeps halving every time. This type of curve is called an exponential curve. So this is critical for understanding radioactive decay. The fact that we lose half the atoms with every half-life. It means that as time goes on, we get less and less parent atoms, more and more daughter atoms. And the ratio between the two, the balance between parent and daughter, is what allows us to work out how old a rock is. But we'll look at that in a little bit more detail in the next lesson. I thought I'd finish by showing you this. I do quite like the sunset colours in it, but this is actually the oldest rock that we now know of in the world. It's a rock called the Acasta gneiss. It's from northern Canada, and it's been dated to be over 4,000 million years old. We can find even some minerals that are older than this. There's a particular mineral called zircon that doesn't change when it gets incorporated into new rocks, and some zircon crystals have been dated to 4.4 billion years old. Okay, we can see that this known rate of radioactive decay, this idea of half-life, allows us to work out the age of rocks. We can actually then put a number on the rock age or geological events. What I want to do next time is show you how we actually go about doing that. I'll see you then.